Bam! Mr. True. In this video, we're going to work through a few word problems or a few application problems involving ellipses. Here's the first one. You'd like to make a door archway that is 10 feet wide and 2 feet tall. How could you use 2 tacks and a piece of string to draw an arc to be cut? So we have this doorway that's 10 feet wide, and I'm not really concerned about how tall the doorway is. We just at the top of this doorway want to build an arch to it, and we want that arch or that archway to be 2 feet tall. So how are you going to be able to draw this perfectly on a construction site just using a tack and 2 tacks and a piece of string? Well, one of the properties of ellipses, and this is just going to be a pretty rough sketch, but one of the properties of ellipses is that when you go from focus point to focus point, you get 2 distances, D1 and D2, and that is a constant sum. So in other words, if I go from focus to graph to focus, I get this white string. If I get, or distance here, if I go from focus to ellipse to focus, these 2 purple segments, or focus to ellipse to focus, no matter how I go from one focus point sort of reflecting off the ellipse and going to the other focus point, the sum of those 2 distances are going to be equal. So D1 plus D2 is a constant number, and so thus a couple of tacks and a string and a pencil will draw you a perfect ellipse every single time if you keep the string tight, and that constant distance is equal to 2a. So this ellipse clearly is wider than it is tall, so we would say that this is a horizontal ellipse. So since the fact that the doorway is 10 feet wide, that means that the length of the major axis is 10 feet. And indeed, 2a is equal to the length of the major axis. So we're going to need a 10-foot string, so that's the first half of the question. To make this archway, I need a 10 feet of string. And now, where am I going to put the tacks at? At the end, how am I going to tack this down? Well, the tacks are going to be the focus points of the ellipse. So we need to find out how far those focus points need to be away from the center of the ellipse. Or maybe not the center of the doorway, because you could think of that being down here, but the center of the ellipse. So what do we have so far? We have an ellipse. The way this is drawn, 2 feet is the distance from the center of the ellipse up to the top. Well, if you're going from center to the end of the minor axis, that is b. So we have a b value equal to 2. And if 2a is the length of the entire major axis, then a, as we know, only goes from center to the vertex, or is half of the major axis. So the fact that this is a 10-foot doorway means that my a value is going to be equal to 5. So the focus points are c units away from the center. From center to vertex is a, center to the end of the minor axis is b, and center to foci points, which is where our tacks need to be, holding this 10-foot string down, are c units away. So in an ellipse, c squared is equal to a squared minus b squared. So c is going to be equal to the square root of a squared, which is going to be 5 squared, minus b squared, which is going to be 2 squared. So that's going to be c is equal to the square root of 25 minus 4, or the square root, of 21. And the square root of 21 is equal to 4.58 feet. So if you're on a construction site and you would like to build a perfect elliptical arch that's 10 feet wide and 2 feet tall, you need to have a 10-foot string, which is equal to the sum of those 2 distances from foci ellipse to foci, and you need to have that 10-foot string tacked down 4.58 feet from the center. And then just the extra slack in that string will be pulled tight with your pencil, move it around, and the top half of your drawing is going to be the arch of this doorway. Bam! Let's get on to the next question. Will a a 10-foot wide truck, which is 12 feet tall, fit through an elliptical tunnel that is 30 feet wide and 13 feet tall? Well, the tunnel is taller than the truck, so clearly it's going to fit, right? Well, it's an elliptical tunnel. That means it has a domed opening or a domed top, which is not uncommon with older tunnels because of the strength of that shape. It's almost like the weight pushing down on it is going to help strengthen the structure. So we have a flat road, we have an elliptical tunnel, which maybe looks something like that. It is 30 feet wide. Yes, that's what I said. 30 feet wide, and it is 12 feet, or excuse me, 13 feet tall. And then through here, we're going to attempt to drive a truck, and I'm going to draw this as it fits, like it fits, I don't really know. But we have a 10-foot wide truck, which is 12 feet tall. Is it going to fit through the tunnel if it stays in its own lane? How are you supposed to figure that out? I mean, I can't go out there and like just run a tape measure up to the roof of the tunnel, and I don't have the truck. Well, we're going to do it with math, right? So we are going to find an equation for this elliptical dome or this elliptical tunnel that the truck is going to try and go through. And to do that, we're going to place that ellipse in the most convenient place possible to simplify the math as much as possible, which means we're going to put the center of that ellipse on the origin. So the center line of the road is like passing right through 0, 0. And in this setup, we have a major axis length of 30 feet, which means that A, which goes from center to the vertex, or the center to the end of the longest axis in an ellipse, which is the major axis from center to vertex, is A. So our A value for this ellipse is going to be equal to 15. And B is the perpendicular direction. B goes from center to the end point of the minor axis, or the shorter axis in an ellipse. And that right there says is 13 feet. Okay, so we have an ellipse whose center, H and K, is at 0, 0. We have a value of A and we have a value of B. So actually, I've already got my equation just about set up. I have all the information for it anyway. This ellipse, at least the top half, is modeled by the equation. It's going horizontally, so we're going to put the x first and put the value of A, which is 15. We're going to put 15 squared underneath the x, and y squared, and put 13 squared underneath the y value, because when an ellipse is longer in the horizontal direction than it is in the vertical direction, we call that, or say that it is a horizontal ellipse, and thus A, coming from the largest denominator, must be underneath the value of x in the equation. So 15 squared is equal to 225, and 13 squared is equal to 169. Okay, so now we have an equation that models this elliptical tunnel, and we're supposed to use that information to figure out if the bridge is going to fit, or excuse me, if the truck is going to fit underneath this bridge or through this tunnel. Well, we know the truck is 12 feet tall, so all we really need to know is how tall is the tunnel 10 feet off of center. And I'm going to do the right side just to keep my values all positive instead of using negative x values. So again, how am I supposed to figure out how tall the bridge is 10 feet off of center? Well, we do have an equation that is modeling this ellipse, and we measure a vertical distance on the xy coordinate plane by looking at the y coordinate. And again, we don't know what that is, but if the truck is to stay in its own lane, this this point right here on the actual tunnel has an x value of 10 and a y value of, the y value is going to be the height of the tunnel. So this is a point of 10, comma, y. The 10 for the width of the truck, and y, which is going to be the height of the tunnel, 10 feet away from the center. And that's going to go in for x and y. that's why we have, that's why every equation has an x and y variable in it to represent any particular point along the graph that we're interested in. So we're going to take out x and plug in that the fact that it's equal to 10. So the x comes out. I'm just doing the erasing here because I don't have too much work to room. Plug in the value of 10, the width of the truck. Remember, it's staying in its own lane. It's pushed over as far as it possibly can, so its left-hand wheels are right on that center line. So x is equal to 10. This is going to be 100 over, 100 over 225 plus y squared over 169 equals 1. This 100 over 225 is going to get subtracted to both sides. We have y squared over 169 equals 1 minus 100 over 225. And then we're going to, let's go ahead and get a decimal for this. Do I have that worked out? I have it in exact form. We can write that out. So we have 100 minus 1 over 225 is equal to 225 over 225 minus 100 over 225. 225 minus 100 is 125. We're going to multiply both sides by 169. So y squared is equal to 125 times 169 over 225. And I don't want y squared, I want y. I want the height of the bridge. So now I'm going to take the square root of both sides of this equation and get y when typed correctly into your calculator all at once. And because I kept this in exact form, there's like 0 round-off error until at the very, very end of the question. The square root of 125 times 169 over 225 is equal to 9.69. So if the bridge 10 feet away from center is only basically 9.7 feet, and the truck is 12 feet tall, it is not going to fit in its own lane. So if it's not going to fit in its own lane, what would happen if the truck were to drive through the center of the road? So let's say instead of being here, the truck lines up and just goes right through the center of the tunnel. Well, if the truck drives right through the center of the tunnel, now where do we care about the height? Do we care about the height of the tunnel 10 feet off of center? Or, let's see, a 10-foot wide truck driving right through the center of the road would mean that 5 feet are to the left and 5 feet are to the right. So if the truck drives through the center of the tunnel and basically just blocks both lanes, what is the height of the tunnel 5 feet off? Will the truck fit there? So let's do this question again, only this time having the x value be 5 instead of it being 10. So part B, center of the road. Okay, well, our equation again was x squared over 225 plus y squared over 169 equals 1. We're going to take x out and replace it with 5 instead of 10. That's going to give us 25 over 225 plus y squared over 169. This time I went ahead and worked it in decimals. I'm going to bring the 25 over 225 and subtract it over to the other side. So that's going to become 1 minus 25 over 225. So that's out. And we get y squared over 169. This is a decimal, comes out to be 0.8889. And multiply both sides by 169. You get y squared is equal to 150.22. And then in your last step, when you square root both sides, now the truck is only 12 feet tall, which is a pretty tall truck, but 12 squared is 144, and my squared value is 150. So I actually already know the truck is going to fit. But when you square root both sides, you get a y value that is equal to 12.26 feet. So, and that's a fairly common application problem because there are a lot of older bridges and older tunnels, even under waterways or over waterways, that are arched like that or domed like that. So if you're a trucking company or a boat company and you're trying to figure out, what are some appropriate paths to follow to make deliveries or to travel, you definitely want to get under those bridges. So that's an example of ellipses and how they apply to trying to get objects through them, such as tunnels, bridges, and so on. Bam! Our last example is a very common application problem in textbooks. It's about Statuary Hall at the Capitol. Another property of ellipses is how energy is reflected from one focus point to another. This has medical applications, and the example in a couple of my textbooks I've used in the past is how they bust up kidney stones to make them easier to pass. They make one kidney stone a focus point on an ellipse, and they emanate this, I believe, ultrasonic energy from the machine, which is from the other ellipse. And so they have this sort of elliptical shape. I'm not a doctor, so I haven't physically seen it in person, but they have this sort of like reflective elliptical chamber, three-dimensional elliptical chamber. They emanate these ultrasonic waves from one focus point, and they place it so that your kidney stone, if you have one, is the other focus point. They try and break it up with these energy waves to make them easier to pass. We're going to do something a little bit more just curious. This reflective property of ellipses allowed John Quincy Adams to eavesdrop on his fellow politicians at the Statuary Hall in the U.S. Capitol building. And I was there one time. They got this huge room, or at least it seemed like when I was there, it was full of tourists mulling around and just checking everything out. And they have these two places marked on the floors with a couple of stands for the tourists. And if you stand at one place and your friend or relative goes and stands at the other one, it's almost like regardless of how quiet they talk, you can still hear them over the hustle and bustle in the rest of the room. And that's because the dome of the room is shaped as a three-dimensional ellipse. And as such, all of their energy, all of their sound waves that they're emanating, whether it hits here or back behind their head or over above your head, any sound that hits the roof of that building is going to be reflected into the other focus points of the ellipse. So it allowed him to eavesdrop on his fellow politicians. How far was his desk placed from the center of that elliptical room that's 96 feet long and 46 feet wide? These values are rounded off a little bit just to make this math I'm doing off the top of my head a little bit easier. So here's John Quincy Adams. He's like, hey man, I can hear everything you're saying. That's awesome. If they were, if these fellow politicians, whether they were, maybe they weren't his fellow, maybe they were the opposite party and he was hoping to use what they said against them. But if there was, some discussion at another desk placed at, or if they were just standing in a certain area of the room, he could hear a lot of what they were saying. And that's because sound waves come up, they hit the elliptical dome, and they bounce off. And this isn't necessarily particularly unique to this problem. Anytime sound or energy hits a solid surface, it's going to be reflected off. That's why there might be a little bit of an echo in these videos, because my voice is bouncing off the back wall, the side walls, the roof, except that this is more of a scattered sound. In the ellipse, no matter if it hits here, here, or here, the sound wave is going to hit that roof, come back, and in calculus you'll be able to find with something called the derivative the slope of a curved line at any given point, and you can show how these opposite angles are actually congruent with a little bit of calculus work that will allow you to find that slope. But we just simply want to find the placement of that desk. Now this is very similar to the first example about tying the string down with the thumbtacks or the nails to draw that ellipse. So maybe you could pause here, I can pause here for a second and see if you can't figure out the focus points of this ellipse, because that's what we did in the first example. Okay, well, this is the long axis, of course, and the long axis is called the major axis in an ellipse, and that major axis has a length of 96. So 2a is equal to 96, or A is equal to 48 feet. And that's also this length over here, but this is the short axis, so 2B, the entire length of the minor axis, is equal to 46 feet. So B is equal to 23 feet. So we have an ellipse. We don't necessarily need the equation. We just need the placement of this desk away from the center of the room. How far away is it placed? Which means I need to know what C is, the distance from between center and focus point. So C squared is equal to A squared minus B squared. And then C is going to equal the square root of 48 squared minus 23 squared. Please do not allow the square root to cancel out those powers of 2, because 48 minus 23, which is what, 25, is not the correct answer. No, the square root of 48 squared minus 23 squared is going to be 42.13 feet. We might want to round it off to 42 feet because the measurements given are also rounded off to the nearest foot. So our calculated average really should be saying that the desk needs to be approximately 42 feet away from the center. So, I'm Mr. Tarou. Bam! Go do your word problems.